Hello all, a warm welcome to the next session in electronic devices. In the previous class we had discussed about one of the kinds of breakdowns that occurs in the reverse bias condition. What was the first breakdown that we discussed? It was about the Zener breakdown that happens. And the effect that takes place is what we call as electron tunneling, which in turn has resulted in what is called as Zener effect. Now, I need to include few more points related to the Zener breakdown. So, the first thing is when we have the heavily doped P and N regions, what is happening? We know that the electron which is present in the filled states in the P-type valence band gets tunneled to the conduction band of the N-type, and this process we refer it as electron tunneling. Done? Now it is very much important for me to represent the distance the electron has to tunnel from the P side valence band to that of the N side conduction band, and that distance is what we refer as D. What is this distance called as? D, which is different from that of the width of the transition region. Don't get confused with these two. Done. And then one key point that you have to understand here is, see, when this electron tunneling is happening, how can I relate that with the covalent bonding I mentioned in the previous class? It is nothing but the breaking of covalent bonds that takes place, which in turn makes the electrons to freely move to the conduction band. Right? So when that happens, if the electrons get break down, if the covalent bond that is present, if it breaks down, the electrons becomes free, the atoms or the molecules that we have tends to lose electrons, right? So if they tend to lose electrons, what will they now become? Instead of becoming neutral atoms, they become charged ions. Yeah, so that's why we say the kind of ionization that is happening is referred as field ionization. Definitely there is ionization process that takes place both in the Zener breakdown and in the Avalanche breakdown. But because of what this ionization is taking place in case of Zener, it is because of the electric field intensity. Since the P and N regions are heavily doped, what happens to the width of the transition region? It is very small, because of which the electric field intensity that is observed in the transition region is heavy. As a result, which helps in the breakdown of the covalent bond, and that's how the field ionization is what being taking place in case of Zener effect. Yeah, so I hope you understood why it is called as field ionization. It's because of the electric field intensity which is high. Why that electric field intensity is high? Because of the heavily doped P and N regions, which makes the transition region width to be smaller. One more thing that I wanted to tell about the Zener breakdown is when I write down the reverse characteristics. This is how I'll be writing the forward characteristics, right? Now when I write down the reverse characteristics, can I extend it for a longer period and then show the reverse saturation current that is flowing? No, this breakdown happens for a smaller voltage, right? Therefore, I have to end somewhere here and then show the increase in the reverse saturation current. If in case I want to represent the Avalanche breakdown, as I mentioned, Avalanche breakdown happens for larger voltages, right? When I provide more amount of negative voltage. So the Avalanche breakdown, if I want to represent, it happens somewhere here, whereas the Zener breakdown happens even before that. Therefore, while writing the graph related to the Zener breakdown, this is how we are supposed to show, and this distance have to be little small. Yeah, so what does this point indicates? It is VBR, and this is your reverse saturation current. So this was about the Zener breakdown. Now let's look into the Avalanche breakdown that takes place. Now, as I mentioned, Avalanche breakdown happens for the voltages which ranges from few volts to that of thousands of volts, right? Now, coming to the regions, how they are basically doped. In case of Zener effect, it was heavily doped, whereas in case of Avalanche breakdown, the P and N regions are lightly doped. We think that the P and N regions are lightly doped. Now, when I assume that we have P and N junctions which are lightly doped, that's why I am not putting any plus mark as a subscript over P or N, which indicates it is not heavily doped. The transition width that is being observed is widened. And what does this indicates? It is the width of the transition region or the space charge region or the depletion region, any way you can call it. Now, how is the electric field direction being represented? This is of, I'll be representing the electric field direction. When these two are lightly doped, when the width is widened, now what will happen when I provide some reverse voltage to this? That means when I connect the P side to the negative terminal of the battery and N side to the positive terminal of the battery, what exactly takes place? Now, as I tend to increase this voltage, what is happening is the minority charge carriers. What is a minority charge carrier in case of P-type material? It is the electrons, right? So, these minority carriers gain enough kinetic energy. See, if in case you have a lean person, if that lean person gets enough food to eat when he is hungry, will he get enough kinetic energy? Will he gain kinetic energy? Yes, he'll gain kinetic energy. Once he gains kinetic energy, will his physical movements become more active, or will it be summoned, or will it be reduced? It will become more active, right? Similarly here, when I am providing certain negative voltage, more and more negative voltage, the electrons which is present in the P-type material gains more amount of kinetic energy. Now, when these electrons gain more amount of kinetic energy, what is happening is these electrons tend to collide with the atoms that is present. As a result, when they collide, they tend to provide or they tend to generate what's called as EHP. An electron hole pair is being generated. Now, how will I represent that electron hole pair? Let me represent an electron with a circle which is filled, and let me represent a hole like this. Done? Now, what is being generated? Because of this electron which is hitting this atom, there is an electron hole pair generated, and this electron now becomes free to move. As a result, how many electrons now resulted in? This electron along with that this electron. Therefore, 2 electrons are now free to move. Done. And these 2 electrons are swept across the positive terminal of the battery, because we know the opposite poles attract each other, right? Now, similarly, here whatever the hole that is present, it gets swept across towards which direction? Towards the P side. Therefore, I will represent the direction like this. Done. This is when I provide a few range of negative voltage. Now, when I tend to increase this negative voltage even further, what will happen? Let me try to write another diagram. So this is figure 1. So let me try to write another diagram which has the width W, the electric field intensity E, this is the P region, this is the N region. Now, what is that happening? The minority carrier is the electron here, which gets hit to an atom. As a result, it generates a electron hole pair, and the electron which is present here moves and swept across to the negative, that is to the N type, and this electron is also moving towards this end. That's why I am writing 2 electrons. Which are the 2 electrons? This 1 electron along with the 1 electron which is generated. Done. And then what is being generated here? A hole is being generated. Now, when this hole comes and contact with another atom, what is happening? An electron hole pair is being generated, and therefore this hole along with this hole, totally 2 holes are swept to the p side material, and this electron that is present tends to hit another atom and generates an EHP pair. As a result, this electron and this electron will move towards the n-type material, and this hole is swept across to the p-type material. Now, when the reverse voltage is not that great, these are the number of electrons that was generated because of the increase in the kinetic energy of a single electron. Done. Now, as I tend to increase the amount of reverse voltage that I am providing, more amount of kinetic energy is gained by the electrons. As a result, it tends to hit the atom. Again, this generated EHP tends to hit another atom. Again, the generated EHP tends to hit another atom. As a result, one single electron is now become how many free electrons we have? There are 4 free electrons is there. Right? So what is happening to the charge carriers? Is it getting increased because of the increase in the reverse voltage? Yes. And this process of increase in the number of electrons, the charge carriers, because of increase in the reverse voltage is what we refer as carrier multiplication. What is multiplication? Increasing the quantity, right? So here, what is the carrier? It's nothing but the electrons and the holes. So the charge carriers are getting multiplied. It is getting increased because of the increase in the reverse bias voltage. And that process is what we refer as carrier multiplication. I hope all of you got these 2 diagrams. Please be careful while writing these diagrams. Clearly mention a filled circle and an empty circle. The empty circle here indicates the hole and the filled circle indicates the electron. Now how this movement happens? So this electron here along with this electron, 2 of them are getting swept to the n side. This hole hits to another atom and 2 holes are resultant in the p side, and there is another electron which is becoming free and hits another atom. Therefore 2 electrons are coming out, and here 1 hole is moving towards the p material. So you have to be careful with the number of holes and electrons you represent in the diagrams. Now, can I try and relate this with the energy band diagram? How can I represent this in the energy band diagram? Let's try to see that now. So be careful here. What is the slope? Should it be steeper? In case of Zener effect, it has to be steeper because the width was very less and then the electric field intensity was more, therefore the slope have to be more steeper. But here it need not to be the case. So you have to be very careful and considering all these factors, you have to write the diagrams. Now because of heating, what is happening? An EHP pair is generated, right? So let me just represent a hole H plus which is getting swept by towards the p-type material, and then electron. So where should the electron move? The hole is with respect to the valence band, please remember, and the electron is with respect to the conduction band. Therefore the electron have to move to the conduction band. Right? So this is the generated hole and the generated electron because of the EHP pair generation. And there is an original electron that is present here. This is an original electron which is present, which also tends to hit and then gets swept across towards the inside material, and that's what I'm trying to represent here. Done? Clear till here? This is the original electron that I am representing and this is the generated electron. There is a difference between these two. Are you clear? So this is about the avalanche breakdown that happens. Now, so if I know this, so this is the process through which the avalanche breakdown is happening. Now once I understand this, is it not important for me to express how quantitatively this carrier multiplication is taking place? So how will I express an equivalent model for this quantitative or an equivalent model for this carrier multiplication that is taking place? Yeah, for that we need to use mathematical expressions, and this mathematical expression goes as follows. So now to express the mathematical terms, we will be using two basic terms. The two basic terms are as follows. One is called as NN and the other is called as P. Now, what does this NN indicates us? The NN indicates the number of electrons that is being provided by the p-type material. Here the minority carriers electrons which is provided by the p-type material, that is what being represented as NN. That is number of electrons from p side. Now, what does this P indicate? It is the probability of the collision that takes place in case of the avalanche breakdown. So, what does this indicate? It is the probability of what does P indicates? It is the probability of having ionizing collision. See, in both of the cases, ionizing basically happens because it is losing electrons, right? So obviously ions or charged particles is being generated. In case of Zener effect, it is the field ionization that takes place. Here the kind of ionization that I refer in case of avalanche breakdown is referred as impact ionization. What is the kind of ionization? In case of avalanche breakdown, it is the impact ionization. So what is the probability of having this impact ionization? It's because of the collision, right? So what is the probability of that collision is being represented by a factor which is called as P. Now, because of this collision, what happens to the number of electrons at the end side? It increases, right? Which is no longer same as that of the number of electrons which is provided from the P side. Therefore, let me represent that term as N out, which indicates the number of electrons at the N side, which is given by Nn plus, I'll tell you what is this. So Nn is the actual number of electrons which is present in the P side. Now, as I increase the reverse bias voltage, what is happening? There is a first collision that takes place, right? So ionizing collision takes place for the first time, and that results in how many number of secondary electrons or the charged particles? That is given by Nn into P. Done? And if this secondary particles again when it collides with the other atoms, there is a tertiary ionizing particles that is being generated. How will I represent that? It is Nn into P square. Again that tertiary will again result in collision with the other atoms and provide Nn into P power cube number of electrons, right? So if I tend to go on, I'll just represent it through the dotted lines. So if I take out the Nn as a common factor, this is what the term I'll be getting, which relates to the number of electrons that is present at the N side is given by Nn into 1 plus P square and so on. What does these terms indicate? This is the first, this is the initial electrons, this is the first collision, this is the second collision, then tertiary collision, and then it goes on. Along with that, I am interested in the carrier multiplication, right? So how will I represent the carrier multiplication of the electrons that takes place? So it is given by N out divided by Nn. So if I take Nn to this N, what will happen? 1 plus P square plus P cube and so on, which in turn can be written as 1 by 1 minus P. Now, the overall probability is what I am considering. Now, what does this indicate as? if the probability of the collision that happens is 100% true, then what is the p value? It becomes 1. So if I substitute that 1 minus 1, it tends to 0. So 1 divided by 0, it is infinite, which indicates infinite amount of carrier multiplication is taking place, which cannot be controlled or which cannot be limited. Done. Now, will the carrier multiplication be only related to the probability of the collision that takes place? No. This carrier multiplication also depends on the reverse bias potential that I am providing across PN junction. Therefore, there is another equation that relates to the reverse bias voltage, which is given by 1 minus V by VBR to the power of N. V indicates the supply, VBR indicates the reverse breakover voltage, and N indicates the exponential term, or the N indicates the exponent term, which varies from 3 to 6 based on the kind of material that I am using to have my P and N type regions. Done? Then, so all these things I hope you are understood. Now there is one more little thing that we have to understand under the avalanche breakdown, that is how this VBR is a function of the doping concentration. Let's try to represent that now. So let me consider this axis to be as ND, that is the donor concentration, how it is measured per centimeter cube. Let me start the axis from 10 power 15, 10 power 16, 10 power 17 andere. 10 power 15 number of donor impurities are added per centimeter cube is what it is indicating, right? And then we have another axis here. This indicates the breakover voltage or breakdown voltage. It starts from 0 up to 10, 10 square, 10 cube. Now let me represent it in a box kind of a structure. And let me assume the temperature that I am providing is 300 Kelvin. That is the room temperature. Now remember, when I provide lower doping concentration, that means the N and P regions are lightly doped. If that is the case, what kind of breakdown happens? It is the avalanche breakdown. So if I say avalanche breakdown, what happens to the reverse breakover voltage that I have to provide? It is more, right? So let me just put a table so that you can understand. So this is avalanche breakdown, this is Zener breakdown. If in case I consider avalanche breakdown, if in case I consider the donor concentration, we know in case of avalanche breakdown the N and P regions are lightly doped. Therefore, I say it to be lightly doped. So ND value is less. Whereas in case of Zener breakdown, it is heavily doped. Therefore, the ND value is more. Done? Now what happens to the VBR? If it is lightly doped, more amount of reverse breakover voltage is required in order to experience avalanche breakdown. Therefore it is more here and it is less here. So up to certain region like this, the avalanche breakdown dominates. After a certain ND value, the Zener breakdown dominates. So if I want to represent that for germanium, the curve goes like this, and this is for germanium. Then comes the silicon, and then the gallium arsenide, and then comes the gallium phosphorus. So after it reaches certain doping, I'll write a curve like this, which indicates that the tunneling, electron tunneling begins, which indicates the Zener breakdown starts happening. This is with respect to ND. Done? And then I consider the temperature to be at 300 Kelvin. So these are all the aspects that you have to cover under avalanche breakdown. I hope all of you are clear with the avalanche breakdown. Now let's move into the next topic in the syllabus, which speaks about rectifiers. Now you have to understand lot more, you have to remember lot more points under rectifiers. So before going into what is rectifiers, let's try to understand few points. Okay. Now when I consider a PN junction, we know that this PN junction operates in two regions. Which are the two regions? It is the forward biased condition and the reverse biased condition. We think of that the forward biased condition is nothing but the device is in the on state, and in the reverse biased condition, even though there is little amount of the drift current that is flowing, we consider it to be as negligible, and we think of that there is no current that is flowing in the reverse biased condition. So if I want to say what are the two regions of operation, one is forward bias region and the second is reverse bias region. If I say in the forward bias, the current, the device is on, the current flows in the device. In the reverse bias, the device is off and the current, there is negligible amount of current that flows in the device. Now, as you can see, in one case the current is flowing, whereas in the other case the current is not flowing. Therefore, such kind of a device, that is the PN junction, is referred as unilateral device. Now what does this unilateral indicates? Uni means one, lateral means direction. So the PN junction is a unilateral device, which indicates that the current will only flow in one direction. How does it flow? It is only from P to N region when I tend to connect it in the forward bias condition. I hope all of you are clear with this. Therefore, we say it as unilateral device. Now, whatever the PN junction that I have is referred by a device which is called as diode. What is that PN junction is called as? It is called as a diode. It is one of the kinds of semiconductor devices which has two terminals, which is anode and cathode. The P type, see if I write like this, then this indicates the semiconductor layered structure. The P type here, that is a P type material, here is represented in this way, whereas the N type is represented by a line here. And how does the current flow? As I mentioned, it is from P to N, and therefore this direction here, this indicates the arrow direction with which the current is flowing. What is this terminal referred as, which is near to the P type? It is referred as anode, and the one which is near to the N type is referred as cathode. And what is this device referred as? A diode. Done. So this is the symbol of the diode, and this is the layered structure of the diode. Now, if I want this diode to operate in the forward bias, what do I need to do? I need to connect the supply like this, right? And this operates under which condition? The forward bias condition. Now if I want the diode to operate in the reverse bias, all I have to do is connect the anode to the negative terminal of the battery and cathode to the positive terminal of the battery, and this condition, let me represent it in the short form as reverse biased. Done. Now if in case I consider ideal condition, done. So under that condition, the forward bias is represented by a short circuit, whereas the reverse bias is represented by an open circuit. How will I represent this short circuit? Let me point these two terminals of the diode. So this is the anode terminal, this is the cathode terminal. Similarly here I'll write it. Now if in case I connect a simple wire between the two ends, then I refer this to be as short circuit. If I leave it open, then I say it to be as open circuit. Now what is this? It's a simple conducting wire, right? So if there is a simple conducting wire which is made up of a metal, then what is the resistance that is offered? It is very minimal. Therefore, what is the resistance in case of a short circuit? It is minimal. If the resistance is minimal, what is the voltage? It is minimal. Current can easily flow, therefore it is maximum. If I consider an open circuit, what happens to the resistance? There is no path between these 2 points. Therefore, the current cannot flow. As a result, I can say that resistance is maximum, the voltage is maximum, and the current is approximately equal to 0, or I can say that it is equal to minimum. Done. So this is how I'll replicate the characteristics, or I'll show the characteristics of short circuit, and this is the characteristics of open circuit. Now why am I writing all these is, now it is my duty to represent the ideal characteristics of this diode when it is under the forward bias condition and when it is under the reverse bias condition. So let me consider 3 cases, out of which case 1 indicates ideal IV characteristics of the diode. If I consider ideal case, how will I represent the forward bias? Short circuit. How will I represent the reverse bias? Open circuit. Keep these points in mind. Now let's try to represent that. This is the diode that I have. I am providing the supply. Let the supply be V. Positive is connected to the anode and negative is connected to the cathode. How the current direction is? It is like this. Just remember, how does this direction points to? That is the way in which the current is flowing in the device. And this current is nothing but the conventional current. It is not the electron current. Done? Now, when I have such a kind of device, ideal diode, so if I want to plot the IV characteristics, voltage is the input and current is the output that I'll be getting. Therefore, I'll consider V in the x-axis, I in the y-axis. Now, what does this region indicate? It is the forward bias region. That is when positive voltage is provided. When the negative voltage is provided, it is indicating as a reverse bias region. Now, let me consider the reverse bias condition. Now, how much ever the voltage I provide, since the resistance is maximum, what is the amount of current that I observe? It is minimal, which I can also say it as approximately equal to 0. Therefore, how much ever negative voltage I provide, what happens to the current? It is 0. Done. Can I show it completely? No, somewhere it breaks down, right? That's why I have completed only till this point. Done. This is regarding the reverse bias condition. Now, when I consider the forward bias condition, what is the resistance? It is almost minimal. We say approximately equal to 0. The voltage is also approximately equal to 0. But what happens to the current? It is maximum. Therefore, even if the voltage is 0, for ideal case I am considering what happens to the current? It is maximum. And this basically defines the ideal IV characteristics of the diode. I hope all of you are clear how to represent this. Done? Now, tell me, is it really possible for us to achieve this characteristics practically? No, it is not possible. Therefore, we need to make some changes in this IV characteristics, and that can be represented by using 2 approximations. So which we refer as second approximation and third approximation. So the case 2 is about the second approximation of the ideal IV characteristics of the diode. So what is case 2? It is the second approximation of IV characteristics of ideal diode. Now how can I show that? As we know, if in case, let me just write it here, if in case I consider a PN junction, there is always a contact potential that exists at the junction. Now what was this contact potential we represented priorly? We represented to be as E naught. Yeah. Now we represent the same term as E naught here, which is referred as offset voltage. What does this offset voltage relates to? It relates to the contact potential which is at the junction. Done. Now, how can I replicate that in the circuit? So what I have to do is, I need to consider the same ideal diode. This is an ideal diode. With that, I will be connecting in series with a battery. And what is the potential or supply to this battery? It is E0. That is the offset voltage. Now let me connect it in the forward bias condition. And how is the current being flown? This is how the current direction is. Done? Clear till with this? Yes? Now, let me try to represent the characteristics for this kind of a circuit. Done. Now, try to understand this circuit. See, I'll just write the same circuit at this end for your understanding. Now, there are two batteries that is being connected. What is this battery? Let me connect it as V supply, or just let me name it as V. That is the input voltage that I am providing, and let me name this as E0, which is the offset voltage, and this is how the current is flowing. Now, what are the two terminals that I have in the diode? It is the anode and the cathode terminals. Now, when I consider anode and the cathode terminals, see here, one key point you have to remember is, I'll just note it down, if K is more positive than anode terminal, then it indicates it is in the reverse bias condition. If the cathode terminal is more positive when compared to that of anode terminal, it is nothing but in the reverse bias. If the K is less positive than anode, then it indicates the forward bias condition. Keep this point in mind. Don't get confused. That's why I'm writing these two statements. Now observe, if the V value that I'm providing is less than the E0, then will my cathode be more positive than the anode? I'll repeat. If V is less than E0, what will happen? K is more positive than anode of the ideal diode. As a result, the device will be in which state? It will be in the reverse biased condition. Done? If in case the supply that I am giving is greater than that of the offset voltage, so that means positive terminal which is connected to the anode is more than that of the positive terminal which is connected to anode. That means the anode is more positive when compared to that of cathode. As a result, this device will be in the forward bias condition. Therefore, K is less positive than anode. Hence, we say the device to be in the forward bias condition. Done? Therefore, remember, this diode will be in the off condition up to E0 value. Once the supply reaches above the E0 value, the device turns on. Now, keeping this in mind, let's try to represent the IV characteristics. Okay. So, if this is your V axis and this is your I axis, then if this point represents E0, when my supply is until V0, will it conduct? No, it will be in the reverse bias. Therefore, I'll represent it like this. Once the supply becomes greater than that of E0, what will happen? The current starts flowing in the device because the device is turned on, and that's how I show the characteristics, which is different from that of the first case, that is the ideal case of the diode. So this was regarding the second case. Now let's consider the third case, which is nothing but the third approximation of IV characteristics for an ideal diode. What does case 3? Case 3 is third approximation of IV characteristics of ideal diode. Now what does this basically indicates is, whatever the straight line that I am using here, it will not be the same, instead it will be a slope. Now why that characteristics exhibit is, if in case I have an ideal diode, for that ideal diode, if I connect the offset through a battery, and then if I have a resistor which is connected, now we know when a resistor is being added, the characteristic that is absorbed becomes linear now, right? It cannot be a straight line, it becomes linear. And if I provide some positive supply, and this is how the current flows, then the characteristics goes as follows. So till E naught, will there be any conduction? No. Right? After E naught, the characteristics that is absorbed is linear in nature, which is a straight line, and there is a slope that exists. How will I represent that slope? dV by di is equal to R. Yeah, that is a function of resistance, and this slope indicates the linear approximation because of the resistance that is involved. So in practical cases, I cannot have an ideal diode. There is certain resistance that is exhibited by the ideal diode, which is referred as a practical diode. So this is how a practical diode is being represented. And this kind of approximation that we have is what we call as piecewise linear approximation. And this been asked in the exam, explain the piecewise linear approximation. That means this is what the case that you are supposed to explain. So check out the marks for which it is being asked. If in case it is being asked for 2 to 3 marks, then if you explain this, it is more than sufficient. If it is for 6 marks, then you have to start with case 1, case 2 and then case 3. Yeah, so we have few more points to be included in this that we'll take up in the next class. Thank you one and all. Have a good day.